Welcome back to the classroom. My name is Mr. Wong, and today we're going to be looking at the methods in making a standard solution. So let's get started. In our previous lesson, we actually talked about what is molar concentration. Remember, molar stands for the number of moles. Concentration stands for how many moles there is within a liter of solution. As we can see, a solution is a mixture of the solute and the solvent, and we're measuring in moles per liter. We previously stated that molar concentration measures the number of moles of solute dissolved in a liter of solution. To find the molar concentration, it's the number of moles divided by volume. Remember, moles in moles and volume in liters. If we want to find the number of moles, given that we already know the concentration and volume, then we can rearrange the formula to look something like so. Okay. We also talked about what is some common household items. So some common household items would have bleach, it would have vinegar, some washing liquid, and each one has its own concentrations, as you can see here. And as you can see, it's a very precise measurement that we use, obviously because different concentrations would have different capacities to do a particular job, and obviously the higher concentration a particular chemical has can also lead to it being more hazardous when using it. So how exactly do we make these solutions? Well, firstly speaking, what you actually see in like shopping centers or regular household items, those chemicals that we use, we actually call that a standard solution. So it's a solution that has a known concentration or accurately known concentration that has already been prepared prior. To prepare a standard solution, you need a couple of things first. You need to know the measurement of the solute, so the mass you use. That you'll probably need an electronic balance. You need to transfer it to a volumetric flask. Obviously, this method is if we're in the lab. In actual industries, it might be a slightly different method. We transfer it to a volumetric flask. This is a volumetric flask. And on a volumetric flask, you can't really see here, but if you see this image here, there's a tiny little line that runs itself across. So that actually shows you the volume of that volumetric flask. If you can get the meniscus just touching that line there, that means you have or as close as accurate amount of the, set amount of volume of that volumetric flask. Once you have the solute, then you need to add distilled water, that's our solvent, to dissolve it to make our solution and fill it up to the marked component here. So this diagram that we have here gives you a nice summary of the following steps required to make a standard solution. So listen through for the tutorial.
You are going to have a pure solid and you're going to weigh it on the electronic balance. Okay, and we're going to use the formula. I'll just write on the screen here. We're going to use the formula N equals to M over NN. And that's going to help us work out how many moles of that product do we have or reactant do we have at the start. And that's the solute we have. Next step is to transfer the substance, so transferring our solute. So now we're transferring our solute into our volumetric flask. You can then wash it with distilled water and then you pour it in. Now, if you have any little bits of solute left in the beaker, remember you need to pour it using the distilled water to get as much out as possible. And for those who ever wondered, do not drink distilled water, it doesn't taste very nice. Statement number 4 is to dissolve the substance in water. So this step we have here. From step 3 to step 4, you'll have a little bottle cap on top. Place that little bottle cap on top, and what you'll do is holding the top of that bottle with your thumb and then your fingers holding the neck. So if I have my fingers wrapped around and then my sort of thumb on top, looks really awkward, but like that. Invert it, so invert up, down. You don't need to shake it. If you shake it, you might have everything spill all over you. So I recommend just invert it a couple of times, and once you see no more solids, then you know it's completely dissolved. Once you've done, add water all the way to the line. Make sure that the meniscus is just touching the line on the volumetric flask. If you do struggle with the final few drops, you can use a plastic pipette, the little droppers, and that can help you out that way. So be a little bit more stress-free. So if I summarize these into actual steps, step 1 when preparing a standard solution, you're going to have whatever substance you're going to use, you're going to put it on an electronic balance, and you're going to record the weight. Now for accurate weights, we'll try and avoid using weights that go to only 1 decimal point. We'll try and use up to 3 decimal points, okay? So that's how we ensure it's really more accurate. These are the standard ones that you'd find in high school. Now, if you go to uni, the measuring tools are way more in-depth and way more precise. And they go from 4 decimal points to even 5 decimal points at times. So step 1, measure the mass of the solute accurately by placing it on an electronic balance. The ones that we have is the top loading balance. Most unis use like the analytical ones, but we do have some at high school as well. Step 2 is to prepare a standard solution. So like I said, what you do is you pour in your solid into the volumetric flask. You can use a funnel in case you spill any solids over. What you then do is use your little squishy bottle of distilled water. You're going to pour that water into the beaker. And you're going to try and rinse it all the way through. You can use a filter funnel to ensure that none of this splashes anywhere. But the final step after you've washed everything out of the beaker is to also ensure you've washed everything out of the filter funnel. If you have a look down here, it says deionized water. Deionized water is the same thing as distilled water. So the exact same thing. Essentially, it's water without any ions, so no calcium, no magnesium, none of the minerals. And then once you're done dissolving everything, fill it up all the way to the line here. You can gently swirl, but you try and invert it. And the mark to show you where you should be stopping is this bit here. Notice, as you can see, some of the liquid has gone over the line, but we determined that to have an accurate measurement of volume, the meniscus at this line here is just touching, and that's when we know we have an accurate measurement of volume. To avoid a thing called the parallax error, which is essentially looking at the volumetric flask at different angles, giving you different interpretation of where the meniscus is to the line, put yourself at eye level to this little line here, and that should avoid you getting any parallax error. So just make sure your eyes nice and close at eye level, or doesn't need to be close, but at eye level looking at this line here. For those of you who might be wondering why the meniscus is shaped like this, that's just to do with surface tension of the liquid. It likes to stick onto the surfaces. If you have liquid mercury, it actually is in the opposite direction. So with liquid mercury, the meniscus kind of goes like a concave up rather than what we have here. Should be convex, sorry. Next bit is, these are just the standard steps. So if you do need to, I'd suggest you copy this down into your book. But it says, use the chemical formula of the primary standard to determine the molar mass of the compound. So like I said, if you go with this, I'll just change to my writing pen. So firstly, you need to find out the mole mass. So you're using N equals to M over MM. Little m is the thing that you measured out. So whatever you measured out with your electronic balance, that's the thing that you're going to put up there. Remember, all of these are in grams. That's in grams. That's in grams per mole, which means number of moles, the units of that is just moles. Molar mass, you can find that on your periodic table, so make sure you use your periodic table for any of these calculations. Step 2, it says use the mass and molar mass of the primary standard. So the very first standard you use to determine the amount in moles dissolved in the volumetric flask. Okay? So that is, again, just this bit over here. This bit at the top, you are just trying to work out the molar mass first. Then last step, use the amount in moles of the primary standard and the volume of the flask to determine the concentration of the standard solution. So that goes to the molarity formula. So that's our molarity formula. And that is C equals to N over V. Remember, concentration molarity is moles per a liter. If you're not sure, I do suggest you to go back to the previous video, as it will give you a bit more explanation of what the molarity formula is.
Okay, so now that we've gone through the summary of the steps of making a standard solution, let's actually take this into the context of if we were in the lab and I want to make a particular solution on a particular concentration. What are the steps that I go through? What calculations do I have to do as well? So the first step is, like we said, we need to record the mass of the solute that we want to put in solution. So in this case, I have 12 grams of pure sodium chloride, and I want to make it into a solution of 250 milliliters. Now the question is, what's the number of moles that I'm using? So we need to go back to our good old friend N equals little m over molar mass, big M, go through there. So the mass we have is 12. The molar mass of sodium chloride, according to the periodic table, is written like so. Okay, we'll put that in 4 sig figs as well. And I find the number of moles I have is 0.20533809 moles per a liter. Okay. The next step I want to find is the concentration of sodium chloride. And to find that, it is the number of moles that I found previously divided by the volume. So that's 250 milliliters, 10 to the power minus 3. And I find that if I round it off to 4 significant figures, it's roughly 0.8216 moles per liter. So that's how you would calculate your mole concentration for your standard solution. You only need a few information: the mass, the mole mass, and concentration or volume. Okay, question 2. Now, most of the time, we don't actually just give you a mass and then you work out the concentration. Usually we actually tell you, I want a 150 milliliter solution, okay, and I want this concentration to be at 0.2 moles per liter. So what mass do I need to make that? So what you need to do, firstly, is to work out using our formula, N equals to CV, to find the number of moles required to perform this concentration. So we have 0.2000, we have a volume 150 10 to the power minus 3 liters, and so we would have 0.03000 moles of potassium iodide used in this calculation. So in terms of the mass of potassium iodide required, that would be 0.03000 times the molar mass of potassium iodide. So that's 0 there, 1, 2, 6, 9. And that means we need exactly 4.980 grams of potassium iodide to perform this calculation or make this solution. Okay, so there's that. Now what we can talk about also is, what if I was to do a dilution? What happened then?
This is just a little simulation depiction of what dilution is. So what is actually happening here? Okay, so we say something is concentrated if there is way more solute in comparison to solvent. If I slowly increase it, let's say now it's a 1-to-1 ratio between the solute and the solvent. It's no longer concentrated. But if I continue to increase the amount of solvent I put in, my solutes are now going to disperse further and further away from each other, and now the solution is diluted. So we're saying it's diluted when there's way more solvents than there is solutes. Okay? The other thing you might take notice of is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, let's just say particles. Let's say if we then dilute our solutions, how many particles do we have left? So after the complete dilution, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 particles again. So let me just write that down for you. So the number of moles, so number of moles when it was concentrated, say it was 15 particles or 15 moles, okay, 15 particles. After dilution, we still have 15 particles. So what does that tell us? It tells us that the value n does not change in a dilution. Okay, so the value for n doesn't actually change, and that actually becomes really important when we're trying to perform our calculations, as it makes life a lot easier for us.
Okay, so in the next video, we are going to look at how to perform dilution calculations and the methods in performing an actual dilution in the lab. Okay, so I'm going to put the links up onto this video here. You can transition yourself to the next video and I will see you there. Take care.